All right, in this lecture, we're going to talk about buffer capacity, pH range, and what happens when you add an acid or base to a buffer. The last lecture, we talked about the definition of a buffer and what it is. So if you're still unfamiliar with buffers, please go back and watch that video and make sure you understand everything. Now, we'll start today with the concept of buffer capacity. Remember, a buffer is something that has a lot of acid in it and a lot of base in it. It's a conjugate acid base pair with all of these things floating around in it, right? Some acids and some bases, and it's best to have them in roughly equal amounts. Now, the buffer capacity is the amount of an acid or base that is being added that the buffer can neutralize before the pH of the buffer itself is changing. Remember, the whole point here is if I'm adding an acid to this, some different acid like HCl, okay, or HF, maybe it's another weak one, doesn't matter, but if I'm adding some other acid here in the form of H plus ions, the base is going to neutralize that, okay? That's the point of a buffer. And you want a lot of the conjugate base around, the A minuses here, to be able to neutralize it. But there's only going to be so much H plus I can add and neutralize the conjugate base here of this buffer. There's only so much I can add before I really diminish the amount of conjugate base there is in the buffer, right? So at some point I keep adding H plus and the pH will start to change drastically in this buffer because there's simply not enough conjugate base left to neutralize the added acid. And the opposite is true if you were adding a base. At some point, the acid part of the buffer will run out or get sufficiently small, and the pH then of the buffer will begin to change to an appreciable degree. So that's the concept of buffer capacity, that there's going to be some amount of acid or base the buffer can neutralize until it's kind of run out of its ability to neutralize things. And it would then make sense that the more concentrated the buffer is, meaning the more HAs and A minuses you have around initially, the greater the buffer capacity will be because the more it can withstand added acid or base. So if we think back to the Henderson-Hasselbalch equation in the previous lecture, right, the pH would be the same of that buffer if we had 1 molar of the conjugate acid and base pairs, or if it was 0.1 molar of each, because the Henderson-Hasselbalch is pH is pKa plus log of acid over base, or sorry, log of base over acid. Right? So if these two numbers are the same, log of 1 goes to 0, and it doesn't matter if those two numbers are both 1 or those two numbers are both 0.1, the pH will be the same because in both cases you'll have log of 1. Right? But the difference is that the buffer capacity of the 1 molar guy will be much greater, right? Because there's lots more of HAs and A minuses around in that buffer to begin with than the 0.1 molar case where there's 10 times less the amount of conjugate acid base pair in that buffer to neutralize some added acid or base. So that's concept one, the buffer capacity. The second concept here is the pH range. And this is the area where the buffer is effective over in terms of the pH. And what should make sense is that sort of the optimal pH of your buffer is when you have equal amounts of the acid and base pair, right? When you're starting out with equal amounts of the acid and base pair, and there's a lot of them, right? We talked about sort of the height of sort of visualizing the amounts of your acid here, which maybe is in red. Oh, try that again here. And the heights of your base in blue, right? So both of these are maybe 1 molar or something. That's ideal. If you come in here and add a little bit of base, then your height of your acid will go down a little bit. And the height of your base will go up a little bit in the buffer because you've added a base to neutralize some of that acid, and now you have more base around and less acid. But it's still pretty close to a 1-to-1 ratio. It'll still be a good buffer. All right, so the optimal pH range is starting out when these two acids and bases in your conjugate acid-base pair are equal, right? If you're making a buffer and they're slightly not equal, that's probably still okay, and the buffer will work effectively. But once you get to an amount of 1, so say the amount of the base here is 10 times the amount of the acid in your buffer, this really isn't going to have great buffering action anymore. Right? If one concentration is 10 times the other, the buffering action here is going to be pretty poor. And when you add acid or base to this, the pH is going to change rapidly. It's not going to be a good buffer anymore. And so the general rule of thumb here is that if one of the concentrations is 10 times the other, the buffering action will be poor. And so the pH range, or the range of pH values that will correspond to, is about plus or minus 1 from the pKa, right? Because thinking back to our Henderson-Hasselbalch equation, if there's a 10 to 1 ratio here of base to acid, okay, log of 10 will be 1. And so this is plus 1. And if it was 10 to 1 in the other direction, like this corresponds to minus 1. And so your pH will be going up or down by 1 in this swing of 10 times base to acid or 10 times acid to base. Okay, from your completely best case scenario of both of these are in a 1-to-1 arrangement where log of 1 is 0, that's where you're at equal values of your acid and base and the optimal pH. Okay, so your pH is going to range from plus or minus 1 from that sort of optimal pH where your buffer is still going to be able to buff. All right, so that's pH range and buffer capacity. Let's do a quick practice problem here and just think about what is the best acid or base to pair with its conjugate salt, okay, which just means it's conjugate acid or base. That'll prepare a buffer with a pH of 9.2. So go ahead and pause the video here and try to think about this. Think about maybe an equation involved for pH of a buffer and how you might use these values to come up with the best acid or base to pair with its conjugate salt in equal concentrations to prepare a buffer with a pH of 9.2. Okay, so there's obviously lots of numbers here. An equation is probably going to be involved. And if it's a buffer pH, I'm probably thinking of using the Henderson-Hasselbalch equation. Which is this. And let me actually, instead of writing B for base, let me just write it in its sort of conjugate acid base pair form. And if it says there's equal concentrations of this conjugate acid and base, then we know the numerator and denominator here are equal. So 10 over 10, for example, or 5 over 5, all of those ratios are just 1, and log of 1 is 0. So here I'm really talking about a buffer where the pH is determined just from the pKa. And I'm told the pH in the problem is 9.2. So really what I want here is a Ka that is going to give me a pH of 9.2, right? And remember the little p here is negative log. So what I'm really looking for here is a Ka that when I plug it in here and take the negative log of it, I get 9.2. Well, you can try that for the Ka given in answer A, and that does not give me 9.2. You can try it for the Ka given in answer D here. That will not give me 9.2. For B and C, I'm given KBs, but we'll remember that we can convert from KB to Ka by doing 10 to the negative 14 divided by Kb. So here, let's do that for option B for ammonia, whose Kb is 1.7 times 10 to the negative 5. So to get the Ka, I do 10 to the negative 14 divided by that value of Kb, and I'll get 5.89 times 10 to the negative 10. That's the Ka for ammonia. And I can plug that into here and see, does that give me 9.2? And when you do that on your calculator, you'll see, yes, that does give me the value of 9.2. So the correct answer here is B. You can try option C as well, convert that Kb to a Ka and plug it in. It will not give you a value of 9.2. So the correct answer here should be ammonia. Now, the last thing we have to get to here is adding a strong acid or strong base to a buffer and actually calculating how that affects the pH. And there's two steps to this. First, you're going to treat it kind of like an acid-base equilibrium problem and determine what's being added, what is it going to react with, and how will that change the concentrations in the buffer. Right? So if we're adding a strong acid to a buffer, that acid is going to neutralize some of the base. If we're adding a strong base to a buffer, that base is going to neutralize some of the acid in the buffer. And so we have to write an equation to represent that. We have to then determine how the values of molarities for the acids and bases are going to change. And then we can worry about what is the new equilibrium values and plug those into the Henderson-Hasselbalch, because it is still a buffer after all, to determine the pH. So let's look at an example of this. A buffer is made by adding 0.3 moles of HC2H3O2 and 0.3 moles of NaC2H3O2 to enough water to make 1 liter of solution. Calculate the pH after 0.02 moles of NaOH are added. The Ka for acetic acid is 1.8 times 10 to the negative 5. Okay, so that's a lot of information. We've read through it once. Let's read through it again and identify what are the acids and what are the bases. A buffer is made by adding 0.3 moles of HC2. So this is clearly the acid. It's leading with H. And NaC2H3O2. This is clearly the base. Right, so in my sort of parlance of just thinking about one of these things in a buffer as being AHA, that is the HC2H3O2. And the A minus here, the base is NaC2H3O2. And in reality, right, Na is a spectator ion, and so this really is just thought about as C2H3O2 minus. That's spectating. And my acid here is HC2H3O2. All right, so those are the two things that are part of the buffer. That is the conjugate acid-base pair. Now, we're also adding NaOH. This is a base. So what we have to think about is writing a reaction, because this will be an equilibrium problem with an ice chart, writing a reaction based on what we're adding and what it's going to react with. So this Na plus is a spectator. I'm just thinking about this as OH minus. So if I think about that I'm adding the OH minus, what is it going to react with in the buffer? A base, OH minus, is going to react with the acid in the buffer. So the chemical reaction I want to write, and this is critical to get right, is that the base that I'm adding, OH minus, is going to react with the acid part of the buffer. And what happens when bases and acids neutralize? Well, we make water. And the conjugate base of the acid that's reacting right? Which makes sense because that is my buffer. That is the conjugate acid-base pair involved in this reaction where I'm adding a base to this buffer. It's going to react with the acid and make the conjugate base, right? But it's critical to get this reaction right. So I would recommend reading through this, identify what the buffer is, what is the acid and base in the buffer, and then am I adding a base like I am here, or am I adding an acid? And I'm adding a base, so I need to write that on the reactant side. That is going to react with the acid part of the conjugate acid-base pair. So now that I have this reaction written, I can worry about my ice chart. And I can use the information in the problem to worry about my initial concentrations, change, and equilibrium. So let's read back through a third time and figure out how much acid and base in the buffer am I starting with. 0.3 moles in 1 liter of the acid. So that's 0.3 molar. and I have 0.3 moles of the conjugate base, which you'll see is on the right side of the equation, but that's okay. That's starting with 0.3 molar. And now I'm adding 0.02 moles to this 1 liter. We're sort of assuming here the volume is not going to change, so this represents 0.02 molarity. And these are all my initial conditions. Now, the whole point of a buffer is that it is going to neutralize this added base or acid, but in this case, we're adding a base. So the buffer is going to neutralize this base, meaning it's going to use up all that OH minus. So at equilibrium, that base has to go to 0. It has to get completely used up. So the change is that OH minus is getting all used up. What is it reacting with to neutralize it? The acid. So that also must be going down by that same amount, which makes sense in the context of our equilibrium chart problems. One of the things on the left side is going down. It's a 1-to-1 ratio in coefficients, so the other reactant is always going down by that amount. And the other side of the equation is going up. And it's a 1-to-1 ratio, so that's going up by 0.02 molars. But in a practical sense, think about what you're doing. You're adding OH minus. It's reacting with this to generate this conjugate base. So yeah, the base gets all used up, OH minus, and in the process is increasing the amount of conjugate base in the buffer, decreasing the amount of the acid in the buffer. So this is the first step that we talked about here. Treat it like an equilibrium stoichiometry problem. All of the added, in our case, in this example, base, it has reacted. What will the new equilibrium concentrations of the buffer be? And now we're at the part of step 2, using the Henderson-Hasselbalch. Okay, so here's a prettier version of this. Okay, this LR is like limiting reactant. We're just using up something completely. Started with the initial. Here's the change. Here's our final. And these are molarities that I am now free to just put into the Henderson-Hasselbalch. This is my base concentration I'm going to put into the numerator of the Henderson-Hasselbalch, and this is my acid concentration. How do I know? Because this is the acid and this is the base. Written a slightly different way here than C2H3O2, but it checks out. So now we plug these values into the Henderson-Hasselbalch. You can put moles here or molarity, doesn't matter. And the pKa, I guess we're not given it in the problem explicit. Oh, yes, we are. The Ka of acetic acid is 1.8 times 10 to the -5. So take the negative log of that to get your pKa. Plug in your base and acid concentrations, divide them out, take the log of that, and all of that magic should get you to a pH of 4.80. Okay, so let's practice this one more time. Remember the strategy here. Identify what's being added, identify what it's going to react with in the buffer, and write the reaction. Then do the ice chart. Figure out what is being completely neutralized and how that changes the concentrations, and plug in your final acid and base concentrations into the Henderson-Hasselbalch equation. So let's practice this here. Feel free to pause the video and try it yourself. If you were instead of NaOH, adding 0.02 moles of HCl instead. Okay, so here we're adding an acid, and so I'm just going to worry about Cl minus being a spectator and think about this as H plus. So what is that H plus going to react with? We know in any acid-base reaction, we're going to make some H2O on the right, and there'll be something else here. And what has to go here is my buffer, right? My conjugate acid-base pair. Remember, here's the acid, here's the base. If I'm adding acid to this buffer, it's going to not react with the acid in the buffer. The acid is going to neutralize the base in the buffer, okay? And so here, maybe I'll write it in the CH3COO minus form instead of the, how it was back here, apologies, C2H3O2. Both of those are equivalent, C2H3O2. So this is the conjugate base that this added HCl is reacting with, and those two things will combine to make the conjugate acid part of my buffer. So here is my reaction. Let's ice chart it up. We're assuming our initial concentrations are the same here. Instead, I'm adding 0.020 moles of H+, still starting with 0.30 molar of the conjugate acid-base pair. The thing I am adding to the solution, in this case HCl or H+, will get completely used up. The conjugate base that it is neutralizing will go down by that same amount. And in this case, it is the acid part of the buffer that is going up. This is now my equilibrium amounts of acid and base. So there's symmetry here with the previous problem. The ice chart numbers look all the same. It's just I have a base on the left and acid on the right instead of a acid on the left and base on the right. So I'm really just flip-flopping the numerator and denominator here in my Henderson-Hasselbalch because I've changed what I've added from a base to an acid. So I'm still going to worry about pH being pKa plus log of base over acid, using these new values of 0.28 now in the numerator and 0.32 now in the denominator. My pKa is still negative log of 1.8 times 10 to the negative 5. Plugging all that in, I should get 4.68. And let's also just, for fun, compare when we added a base to the buffer. The pH was going up some from 4.74. When I added acid to the buffer, the pH went down by a little bit. So it's resisting a large swing in pH, but it still does change a little because I've added acid, the pH went down, versus when I added base, the pH went up. Okay, so that'll do it on this lecture covering buffer capacity, pH range, and how to solve problems where you're adding an acid or base to a buffer. And this really sets us up for the next series of lectures here on titrations, where we'll be adding an acid or base, creating a buffered system, and getting a little bit more complicated with the math of how to solve titration problems. But it really does build on this equilibrium approach, figuring out what's neutralizing what, and concentrating on getting the reaction right to begin with. So that'll do it for this lecture. See you next time.